All right, good deal. So last time we left off with these qualitative examples of load transfer. All right, so we looked at this cantilever beam, right, where there's an off-center load that's parallel to the length of the beam element. All right, so that's similar to this situation up here. Now we're going to look at this condition where we have a cantilever element. This time it's oriented vertically, and there is an off-center load at the free end that is perpendicular to the length of that element. So thinking through this, all right, so now if we think about what reactions we have at play, I meant to do this earlier, blocking my view. If you think about the reactions at play, right, of course, after we apply the load transfer, that moves the point load to the center, and then we have to add a torque about the longitudinal axis. So our reactions will include a shear force, right? It'll include a torque. And then it's also going to generate a moment about the y-axis here. So if we extend this line to represent the y-axis, all right, we would also have a reaction that is moment about y. And that would just be equal to P times the length of that element, right? So I'll go ahead and note that here, that we'll call that length L. So if we sketch shear and moment diagrams for each of these forces, all right, that are going to be acting along the length, all right, the shear would be acting in the z direction, right? So that's the direction of the applied load. So we could call that Vz. And that would just be constant magnitude of P. The moment, all right, so this is your My. All right, we would have a maximum value at the fixed support. So that's where it would be equal to P times L. And then it would be a linear decrease to 0 at the free end. And then the torque, this would be torque about the x-axis, right? Torque would be constant along the length. So considering each of these, all right, the shear force will generate shear stress. So we'll say tau, it would be in the xz plane, would be the greatest at the center of the cross-section, right, if the cross-section is solid. Bless you. From the bending moment My, we would have a normal stress, sigma x. And that would be the greatest at the extreme fibers of the cross-section in the z direction. All right, so the extreme fibers, because it's moment about y, it would be the greatest at the extreme fibers in the z direction at the base. And then from the torque, we would get a shear stress that would be greatest value at the extreme fibers in the cross section all the way around. Any questions? All right, so again, we're just doing qualitative assessment of stresses, yes?
Why in the Z direction?
For sigma x?
Yeah.
So the location, so we're identifying the location where sigma x would be greatest, right, within the cross section. So because the moment is bending about the y-axis, that's going to cause compression at this end and tension at that end in the z direction, right? All right, so we can conclude from this qualitative assessment that the most severe stress is likely going to be at the base, right? That's where we have maximum my, and then since the other two are constant, it'll definitely be at the base, right? And we can conclude that it should be in the extreme fibers in the z direction. Does that make sense to everybody? Okay, cool. All right, so now just gonna have a couple notes on axes. So in this class, we'll be dealing with a lot of, three-dimensional and planar notations. So generally speaking, the x direction is oriented along the length of an element, right? It's not necessarily horizontal. So we'll try to keep it consistent with the longitudinal axis. And then the other two, all right, so then I'll say then you have y and z is your cross-section plane. All right, so we'll complete that. So if you have a axial force, then of course that would cause normal stress in the x direction. And then if you had bending about the y or z axes, that would also cause a sigma x in the longitudinal direction.
Quick question on
Yep.
just our observation of the extreme fibers in the z direction.
Sure.
I get why it's at the base. I'm just not sure why we can say it's in the z direction, because isn't the shear and the torque causing it, they're not causing any stress about the z direction, right?
Okay, sure. So so the reason I came to the conclusion that it'll be likely in the z direction is mainly due to the fact that this is where that normal stress will be greatest. The torsional, the shear stress due to torsion, that's going to be constant in all locations around the cross section, right?
Right.
So if we just consider one of those extreme points due to my, we have nothing less from this guy at those locations, and then from the shear, right? So VZ, that's going to have zero stress at the extreme fibers, right? So that's not going to really play into it. So you have to kind of mentally balance the fact that this transverse shear is going to be kind of a separate player when we consider
Right.
extreme locations. Yeah.
Okay,
Yeah. Does that help though?
I think so.
Okay. Yeah. So it's mainly due to these two. Again, if we had actual numbers, we would know whether. I mean, it's unlikely that the center would have a greater overall stress state just due to shear, because you would have 0 my at the center, right? And you'd have
Right.
0 torque at the center, or zero shear stress due to torque at the center, right?
Okay.
So with these two going to 0 where this is the greatest, it just leads us to conclude that the greatest stress will be where these two coincide.
Okay.
Yeah. Yeah, good question. All right. So now we've got this handout that just summarizes a bunch of information on stress. So all of this is stuff that you have probably seen before in mechanics of materials, maybe not as detailed as some of these shear stress diagrams. I guess it depends on how much you got into it in that class. So, but we'll go into this more in a later lecture. But for now, right, just consider this a nice reference handout with a bunch of information on stresses. And then here's where you can find, right, a refresher on bending shear stress and how you calculate that first moment of the area, right? So this Y1 is a variable distance, and it's always measured from the neutral axis to the point where the shear stress is being calculated. And then that area A1 is defined based on that position. So then Y bar, right, is also dependent on Y1. It's the distance from the neutral axis to the centroid of that area. So I'll just note then that these two, all right, these vary with Y1, which is your variable. So in this equation for shear stress, right, V and IZ would be constant for a given location along the length of an element, but Q and B, or switch colors here, all right, Q and B can vary. So I'd say this varies with Y, because B is the width of the cross-section material. So if the cross-section is not, right, symmetric, like, or I guess this is symmetric, but you know what I mean. If the cross-section is not like a rectangle or a square or something, then B can change with depth. All right. And then on your next page, it's just got some more stuff about torsion. You got solid circular shaft, hollow circular shaft. So this is providing section properties, right? Moment of inertia, cross-sectional area. So again, a nice sheet to reference if you need to pull those equations from somewhere for a problem. And then pressure vessels, right? So we talked last time about some hoop stresses and longitudinal stresses. So you've got these just all included on that reference sheet. And then going on to plane stress and the stress transformation equations. So these should all, again, be familiar. You should have seen them in mechanics of materials. We have a similar set from of the transformation equations for strain. So there's a similar handout in the strain lecture that will include those. So the strain transformation equations, I don't expect that you've seen before. I don't think those are typically covered in mechanics of materials, but I guess it maybe depends on who taught you. So, but the stresses is definitely, that's something that you've seen, right? And then here are your constitutive equations, right, relating stress to strain for plane stress conditions. And then we've got here just a summary of different loads applied to a cantilever beam and the stresses that you could expect to see at the support. So that's showing shear stresses and normal stresses in there. All right, so that brings me to homework 1. So the first 2 problems are related to stresses. All right, this first problem is a combined stress scenario. So it's similar to what we looked at qualitatively on Wednesday, but now you have numbers to use. All right, so you just calculate what stresses are caused by each of these individual loads. So you'll end up with, some of them will generate a sigma X, maybe a sigma Y, and maybe a shear stress, right? So document all of those and then add them together, right? Superimpose them so you end up with a state that has one value for sigma X, one value for sigma Y, and then a shear stress. Answers are given to you, so you're just asked to confirm that those are correct, right? Show the work. And then for your shear stress calculation, because it's a thin circular section, that calculation for Q, the first moment of area, is not as straightforward, right? So you're given the equation here based on these values, okay? So you can use that. And then the second problem is combined loading and load transfer. So here, or I guess really just load transfer, okay? So there's one load applied to this system at the corner labeled E. And so you're asked to confirm that these are the resulting stresses at the corner points at the base, all right? So you'll want to just take that load, transfer it to the center, which is on this y-axis, all right, that lands in the middle of the footprint. And then determine what moments that causes about X and Z, all right? So it'll generate a moment about both of those axes because you have to move it in 2 orthogonal directions to get to the centroid. And then based on that axial force and then those generated moments, calculate what those stresses are. All right, so then the next 2 problems are tied to strain. So I'll come back to those after we get through the strain lecture. But any questions so far on stresses? Okay. So for normal strain, all right, and a lot of this should be review. Not the entire lecture, but the beginning anyway. Of course, normal strain corresponds to normal stress. All right, and it represents change in length per unit length. So it's technically dimensionless, all right? Units would be length per length. We still often represent them with those units, but it's not necessary. Sometimes it's also represented as a percentage. A positive normal strain represents extension, and a negative normal strain represents contraction. And typically these are very small. All right, less than about 0.005 maybe we can attach units to it, inch per inch, say, or 0.5%. Shear strain, of course, corresponds to shear stress. and it represents a change in angle from 90 degrees. It's measured in radians, which is also dimensionless, right? A radian is length per length. It's like arc length divided by radius, right? So positive shear strain, which we use the Greek letter lowercase gamma for it. So if we call this, we'll just call this point O. We'll say positive shear strain is that the angle at a point, right, we'll call that O, decreases as shown in this image. If we have a negative shear strain, that means the angle has increased. And once again, these values are usually very small for most materials. So a lot of times we approximate it by taking just the tangent of the angle. All right, and as you know, stress and strain are related through material properties. So stress is used to evaluate a material's ability to carry applied loads, but it can't be directly measured. So because we can't directly measure it, we calculate it from other measurable quantities like force or strain. All right, so you remember these equations, of course. All right, where capital E represents Young's modulus. Okay. All right, so now moving on to strain measurements. We'll use strain gauges to measure strains. And as an example here, all right, we have some strain gauges, 3 strain gauges, A, B, and C, oriented as shown. And we're asked to find the strains at point O, which is not labeled. That's supposed to be this point right here, from the strain gauge readings, right? So first of all, of course, it is most convenient and efficient to orient strain gauges so that 2 of them are aligned with the orthogonal directions that you wish to measure directly. So then that way, like in this example, right, we can just directly measure the strain in Y from gauge A reading and the strain in X from the gauge C reading. All right, so strain in X is just equal to the strain gauge reading from gauge C, which is given as negative 700 times 10 to the minus 6. And strain in Y is just going to be directly measured by strain gauge A, which is 600 times 10 to the minus 6. Now that leaves us with the shear strain that we haven't yet measured. The shear strain can't be directly measured using strain gauges, so we need to calculate it using the strain transformation equation. And that's the reason we need this third strain gauge at an angle. So we're going to label this, or it's already been labeled, right? So this axis, we're calling that X1. And if you look on the next page, or not the next page, 2 pages, 3 pages out, sorry. So on the second page of the handout, all right, is the strain transformation equations. This is what I said, we have similar to stress transformation equations. So this is the equation that we're using in the example. It gives us a way to, so it's solved in terms of an axis X1 that's at an angle to our X and Y axes, all right? And so since we already know the normal strains in X and Y, and we have a gauge acting along this X1 axis, we can just then plug those in and solve for the third unknown in that equation, which is gamma xy, all right? So that's what we'll use in this equation. So I'll just say for gamma xy, can't directly measure it. So we'll use strain transformation. All right, so we've got that normal strain measured in the B, or the B gauge, which is in that X1 direction. All right, so epsilon B is equal to epsilon of X1. And then plugging in values for our, let's see, well, I'll go ahead and set that equal to the value. So 200 times 10 to the minus 6. And that's equal to normal strain in X, cosine squared theta. I'll go ahead and write out the symbolic version, since that's what I expect you guys to do in your homework. All right, so then plugging in those values. All right, we know that. There's like negative 700 times 10 to the minus 6, 600 times 10 to the minus 6. And then theta was given as 45 degrees. All right. So then you can solve for gamma xy. And you should get 500 times 10 to the minus 6 radians. All right, so now that you know the normal strains and the shear strain, you can use Hooke's law to calculate the normal and shear stresses, right? questions? Okay. Anyone still need to see it? Let me know if I'm moving too fast. Okay. All right. So now we'll talk about strain displacement equations for plane conditions. So first up, we've got a general sketch to represent plane stress versus plane strain. All right, so with plane stress, this is representative of a thin body. All right, where the normal stress in the z direction would be 0, okay? But the normal strain in the z direction is not equal to 0. All right, so you remember from mechanics of materials, if you have a thin plate like this and you have normal stresses applied in x and or y, it will cause a change in thickness of that plate, right? So we can't say that the normal strain in z is 0. It's not. With a thick body, however, all right, so this would be a plane strain, we have the opposite, all right? So normal strain in z is essentially 0, and the normal stress in z is not 0. In fact, it would be equal to Poisson's ratio, which is that Greek letter nu, times the sum of the normal stresses in x and y. So let's see. All right, so I'll stick with the thick body for now. All right, so we've got strain in y and x, but not in z. And this thick body would be idealized as a long wire with stresses acting perpendicular to its length. So if you can imagine this chunk as just being one piece of a really long element, right? So we'd have no strain in that direction, right? And the stresses would be acting perpendicular to that length. So I'll write that out. And I realized that in this little example, I just violated my axes guidelines that I told you about. So in this situation, I'm referring to length in the z direction. All right, so then back to plane stress. Here we've got stresses that act along the xy plane, but not perpendicular to the plate. And just summarizing what I said earlier, right? The plate can change thickness. All right, so I'm going to truncate that thought, and we're going to move on to the bottom half of the page here. So this is where I'm going to break down the relationship between strain and displacement. And this is going to be directly relevant to one of your homework problems. So I'll explain why once I'm done going through this. But first, we're considering this originally rectangular element having undergone some displacement and deformation is now in the displaced and deformed shape shown in pink. So we have our x direction and our y direction identified, okay, and u is the variable that we will use to represent a change in x. So I say change in x displacement. And v will represent, or I guess it's kind of redundant to say change in x displacement. That's not what I'm trying to say. I'll just say u is equal to x displacement and v is equal to y displacement. All right, that's simpler. All right, so the original lengths are noted as dx and dy in the xy directions. Now, after being displaced, right, so it undergoes rigid body translation and then also deformation. So there's no strain as a result of the rigid body translation, right? The strain only comes from the deformation because it's the change in length divided by the original length. So I'll note that down over here as well. So strain is change in length divided by original. All right, so this distance right here, all right, we'll track this point. All right, so we'll call that U1 as the displacement of that corner in the x direction, and V1 will represent the vertical displacement of that corner. Now, if we look at this corner over here, all right, this distance is not the same as U1, right? It's a little bit larger. So this is going to be U1 plus however much it has deformed with respect to x along that length. So we'll call that the change in displacement in the x direction with respect to x applied over the original length dx. So I'm actually meaning to write these technically as partial derivatives, right? Because u and v can be functions of both x and y, okay? So this is a partial derivative of u with respect to x applied over the original length dx. So I'm now going to label this angle. All right, I'm going to call that alpha. And then we'll define this vertical distance here, the change in position of that corner. So this is going to be equal to V1 plus the partial derivative of V with respect to x applied over the length dx. So that is representing, I'm going to use a highlighter here. This term is representing this portion of the displacement, all right? Because this portion right here is just our V1. All right, so now if we apply the same thought process to this corner up here, I'm going to go ahead and mark the angle. So I'll call this angle beta. We'll come back to those angles when we do shear strain. All right, so this distance from the original position to the final position of that corner in the x direction is going to be u1, all right, so that rigid body translation plus the deformation that occurs in the x direction with respect to the y, all right, because this is the originally vertical side. So that's going to be partial derivative of u with respect to y applied over the original length dy. And this portion represents that piece. All right, we're almost done. We still have this guy to do. So this is going to be v1 plus the partial derivative of v with respect to y applied over the original length dy. All right, so now that we've identified all of those items, all right, we don't have to do the fourth corner. We could, but that would be excessive. We don't need it. We can now define our normal strain equations and shear strain in terms of u and v and x and y. All right, so the normal strain, we have the change in length divided by original length. All right, so the change in length in x is u1 plus partial derivative of u with respect to x dx minus u1. All right, so we're just taking this minus this for our change in length. Original length is dx, and so that simplifies to just the partial derivative of u with respect to x. Similarly, the normal strain in y, we're going to take this minus this. All right, so that's v1 plus dv dy dy minus v1 divided by dy, which gives us partial derivative of v with respect to y. Bless you. All right, now shear strain, I'm going to come down here for that. So gamma xy represents, again, the change in angle from 90 degrees. So is that change in the angle, if we consider this lower left point, is that change in angle, or is that shear strain, is what I want to ask, going to be positive or negative based on the shape shown?
Positive.
Right, it's positive because it decreased in angle. So and in this case, that's going to be equal to alpha plus beta is the value of that shear strain. And for small angles, all right, so we're going to apply the small angle theory. All right, the tangent of an angle is approximated as being equal to the angle. All right. So following that approach, all right, we have for alpha, all right, here is going to be our tangent of the angle. This term divided by dx, all right? So we've got partial derivative of v with respect to x dx divided by dx. plus beta, which is going to be this term right here. Oops. All right, so this divided by dy. So that's partial derivative of u with respect to y, dy divided by dy. And that simplifies to partial derivative of v with respect to x plus the partial derivative of u with respect to y. So that's using that small angle theory, tangent alpha is equal to alpha, and this is from tangent beta being equal to beta. Questions? All right, so now we're close to being done, and this is the perfect time. I don't really need to talk through this handout. Again, it's just a nice summary of strain information. Strain gauges, if you want to see the actual strain gauges that generated this handout, I've got them up here. You can pass them around if you want. And then I just want to take a minute to talk then about the homework on strain and how it ties to that one example that we just looked at. So second problem is just going to be using strain transformation equations to figure out strains from strain gauge readings. And then the first problem, this is what is tied directly to those equations that we just derived, right? So here you have this plate that is rigidly attached along two sides, but it's free to deform on the other two sides, all right? So only one corner can displace. And so this corner D is displaced in 1 inch in both directions. So you're asked to use the information given here in conjunction with the fact that the equations for u and v, which again represent the displacement in x and y respectively. So you need to find the constants, a naught, a1, a2, and a3, and b, and so on. You need to find those constants using the information given here. And then once you have found equations for u and v in terms of x and y, then calculate the strains using those formulas that we derived, all right? So my advice to you, right, is to think about this, right? X and y represent coordinates, right, so of a point. So we'll say x, y, original, we'll say that represents the original coordinate of the undeformed shape. Original coordinate of a point, right, of the undeformed shape. So you have points that you can work with, all right? So B coordinate is 0, 0. So that's one point that you can plug into this equation, right? And you know what U is, right? U and V in these cases are known for A, B, C, and D, or A, whatever, right? So A, B, and C have a U and a V of 0, right? But D has a U and a V of 1. So using that information, and you have 4 different points where X and Y are known, you can solve for those constants, okay? And then you'll have the full equation, so you can use that equation to find U and V for any point within that plate, all right? So that's my advice. Start with point B. Because xy is equal to 0, 0, and that's the easiest place to start. Okay.
And we're just solving system equations for the A naught, A1, A2, A3?
Yeah.
Because U and V is 0 at all those points, at A, B, and C.
A, B, and C, yeah, right? So U and V represent the displacements in X and Y. So since those points are all tied to the support, they won't displace, right? Yep. All right, good deal. Questions, comments, concerns? Okay. Well, with that, I will send you off and have a great weekend. See you Monday. In Roberts 390.